Hi, everyone. Myself, Arup, and with me, Niranjan. We are from Mindtech. So, just to set the context, the data is growing in big volume as we speak, everyday basis, right? The data is growing in big size as we speak. So the different technologies, right? The IoT, the big data, the 5G, on all these various technologies are pushing the volume of the data. And the data is getting stored. And of course, the storage capacity requirements are also growing with the advent of all these various technologies. Right, that is what is the reality on the technology horizon. Now, with all this is happening, and there is another interesting thing which is happening is the AI and analytics. So that is actually forcing the community to keep the data, store the data for a longer period, and extract value out of the data. Right. So in a sense, the data storage requirements are growing very, very fast, and that is demanding the storage in big volume. Now, once that happens, then the cost that is incurred vis-a-vis the performance that we get out of the storage, that becomes an important factor to be considered. And the innovation is ongoing on a constant basis towards ensuring that how the cost can be brought down, and while enhancing the performance of this disk. When I mention performance, how well we can access, how fast we can access, the access speed makes a difference. The longevity of the drive makes a difference. And the overall performance, that also makes a difference. So these are the factors actually we considered, and then there are innovations going on in this storage space, as we speak. Now, what we have picked up, I think Niranjan, you can go to the next slide. So one of the technologies, ZNS, that we picked up, which is in this endeavor of bringing the cost down while enhancing the performance, right? So that is what our topic of discussion. We have been nurturing this technology for some time. We are a services company, solution and services company. So we support our customers in this technology space, and in ZNS in particular, we have been working for some time. So in today's discussion, actually, we will go into a bit more details about ZNS. Let me give a macro view about ZNS first, and then my colleague Niranjan will take you through more technical details about ZNS, right? So this is the agenda that we are going to cover in this presentation: evolution of ZNS and what exactly ZNS is, why we are using or having ZNS, what benefits it is giving, then who are the prominent and main vendors in ZNS today, and many more are getting added to it in any case. Then the ZNS architecture and what exactly is the zone and how is this zone managed. There are zone states, those things will be defined, and then what are the different ZNS drive types. So these are the items which will be discussed in this particular session. Move on. Niranjan. So before we jump into ZNS as a technology, so let me quickly talk about the traditional SSDs that is there. We are already using this SSDs for some time now. And the SSD, the way it works is that the NAND flash section has got a controller, And then on top of that, there is a software which is called the flash translation layer that essentially manages the nuances, the details about the NAND flash cells underneath. And also it sort of maps the logical addressing which comes from the top, from the applications and the host to down to the physical media. So that it does, and it does a lot of other activities, which is garbage collection. So when the memory cells get used up and some file, suppose erases, the file gets erased, and then some cells gets emptied, and so to recollect that, so we do a garbage collection. So that is that activity in the disk is managed by this FTL. Then where leveling. So every time the write happens, so where happens. So there is a where leveling implemented to protect that. So that where leveling management, error management, and media management. So all these activities are done by the FTL layer, which is sitting on top of the media in the conventional SSDs. Now, what happens is that, this FTL, it manages, but in the process of doing that, see, when the complicated workloads operate on this storage, assuming multiple users operate one disk, or in the cloud scenario where same application is used by multiple users or few users are operating on multiple applications. So what happens is that the write on the disk, that gets repeated multiple times. So it is, and that creates something called the write amplification. So meaning, once one file writes onto the disk, and again on the same flash cells, again repeated writing happens, and that how many times it gets written in average on the disk, that defines the write amplification factor. And that really grows, and it becomes higher in different working scenarios, right? So that is one rather a problem which is there. And then to counter that, there are space amplification which also happens. So we do, over provisioning, and then also the space amplification happens. So these are the two, what you call the problem areas, or under different workload conditions, these are two problem areas which come up. And that essentially what it does is that it jacks up the effective cost of the drive per usage of the gigabits of data, right? So that's what really happens. So to circumvent that, or to improve over that scenario, there are new specifications which has come in from NVMe working group. So there is an extension of NVMe working group, and they suggested, so there are plenty suggestions from this group as part of the worldwide innovation driven by multiple giant companies. And then one of these kind of value adds is ZNS, and this is a specification which to some extent solves or overcomes this problem. So in ZNS, basically what we do is that we bring in the host to participate into the orchestration. So the host shares some load of the drive, so which the FTL was doing it onto the drive. So some part of the load is taken over by host, and host manages certain things like garbage collection, etc., and relieves off the FTL or the firmware on the drive to do certain task, which is basically helps in reducing the write amplification and space amplification. Next slide, Ranjan. Well, so here, we talk about what really ZNS is. Niranjan would talk in more details, so I'm just giving a top view here. So what really happens is that in the conventional SSDs, once the files write, suppose multiple files are writing onto the SSDs, and these files may have different life cycles or lifetime, so to say. So one particular file having a shorter lifespan might have got deleted. So once it gets deleted, what happens is that those cells which were occupied by this file, cannot be used up unless that erase unit is erased completely, and then those cells are reused again, right? And in effect, if you do that, multiple times garbage collection, what happens is that the space that is the over provisioning really happens. So if you look at this diagram on the left side corner, the bottom part, the pink color section, the bottom part of it is the over provisioning. So that essentially is the space which is extra space needed for the actual for the disk actually. So essentially we are paying more for the capacity which we are using from the disk, right? So that's really happens in the conventional SSDs. So in ZNS, what happens is that this is really distributed with zones. So in the namespace, the blocks of zones are defined, and the whole space, the media space, is filled up with zones. And then in the zones, one condition is that it is a sequential write condition. The reading can be done at random the way we want, but the writing has to be sequential. So what happens is that here, the whole garbage collection part of it. So when some delete happens, the whole zone can be reset to rewrite it, right? So that way, a lot of these garbage collection activities, which is taken up by the host, and it is not really left to the local drive to manage it. And thereby, the over provisioning comes down. So if you look at it, the over provisioning in the ZNS area is almost tending to zero. So that is the benefit of the ZNS, right? So in a sense, the garbage collection and then high-level error management, etc., are kept at the host, and then SSD firmware primarily, handles the wear leveling and the media management, right? So these activities are kept with the drive. Now, essentially, out of these whole ZNS implementation, so the space amplification and the write amplification both reduces, and thereby it gives a tremendous cost advantage. So the cost incurred for each gigabytes of disk space, that comes down, right? And typically it comes down to the extent of, close to 10 to 20%, in some cases 30%, depending upon under what environmental condition the conventional disk versus the ZNS is used. Let's move on to the next one. So why we use ZNS? Of course, the first factor is the cost. It reduces the cost quite substantially vis-a-vis the conventional SSDs, right? And then another thing happens is that since this garbage collection and some of the other functions are taken by host, so it really pushes the NAND vendors, to be more competitive. So they can churn their product much faster. They can really release their product much faster. So that is another advantage. And then better control on the over provisioning that I mentioned and the RAID. So the cost improves that I mentioned. And then the write amplification write amplification basically, reduces. And then the life of the disk goes up. So basically, once more write happens, obviously the disk life, gets impacted. So if we can reduce the write amplification, the SSD life also, as a result, really goes up. So that is one benefit for which we are going for ZNS. Then second benefit is that, the QoS and the tail latency, that becomes better. Tail latency, as I mentioned, so the garbage collection happens from time to time, even though the performance remains steady in a steady period. But whenever the garbage collection gets triggered, obviously the performance drops. And with ZNS, this particular problem of conventional SSDs are taken care adequately. So it reduces this tail latency and makes it better. And then the QoS, the quality of service for the complete disk to the application, so that also goes up. Okay, so this is the second benefit from ZNS. And then the third one is that this new NAND types by the vendors. That is another area which I sort of mentioned earlier. So that becomes better because the testing effort reduces for the new NAND vendors for their product, because a lot of functionalities are taken away. So they only concentrate on the functionalities which are kept with the SSDs. So they can churn these products much faster. And in an installation also, to some extent, the dependency on particular type of vendor also reduces quite an extent. So it can be very more agnostic in that sense. And with the advent of cloud, ZNS helps in optimal usage in the cloud scenario. So in the cloud host operation and in the cloud implementation, it works in a much better way. So these are some of the benefits of ZNS. Move on, Niranjan. Yeah, so few vendors were very, very advanced already, and they already have products with ZNS, and there are many other vendors who are already operating on. Samsung, WDC stand out, and then with this, SK Hynix and Kioxia, these are the companies also we know of. They have their own drives, and so these are some of the vendors, and I'm sure more vendors will jump into this bandwagon of coming up with the ZNS SDDs in the coming days. If not, some more are already having this, right? Yeah, so over to you, Niranjan. Go to the next slide. I guess from here, you'll have to take it forward, right?
Yep. Thanks, Arup. Continuing with what Arup said, now I'm going to talk about the ZNS architecture-wise. On a high level, I'm going to talk about what is there in the host software and what are the new commands that are being added with respect to the zones, the identify commands, some NVMe commands like the zone management send. If you see on the host part of it here, the zone management receive, zone append, copy and commit. There are some ID commands like ZNS number of active, that will identify the number of active zones, number of open zones, the characteristics of the zones, the read-write commit, read-write size, and the maximum read-write readable areas. So here on the right side, what you're going to see is there are a number of technical proposals that are going on, which talks about the endurance group management, zone management, namespace types, simple copy, and the random write area of the zone, ZRWA. So at the firmware level, still it remains the same. As Arup pointed out, there are some media management, and he also spoke about some features called as multi-stream and fail in place that could happen. So if you see here at the SSD firmware level, to some extent we have mapping and wear leveling, not complete, but the wear leveling is moved to the host side. To some extent we have here. Also on the disk firmware side, we see the zone info here. So let's say on some host, if we do so there are there's something called as PEG NVMe control command, which is going to tell us the total number of zones, zone type, zone state, zone attributes here. It also talks about the write pointer and the zone start LBA that we can see. So this is a block diagram that depicts on what was happening in a conventional SSD, what was happening at the disk firmware level. Here on the left side, if you see, there is that's in blue. We see the address mapping, data placement, garbage collection, where leveling, and namespace stream reservations that are happening at the disk firmware level. That gets moved to a new code on the host side here, just above the NVMe driver and just below the block driver. That code, I mean, what's happening here, that gets moved on to the host side of it, which will help the SSD firmware in reducing the write amplification and space amplification, as pointed out by Arup earlier. But the error handling and the media management still remains at the SSD firmware level. So this is a high level pictorial representation of the SDF FTL here, if you see. So this is at the low level, and this is from the top level you're going to see. So the SDF SSD is having multiple partitions here, and each partition is going to have a random write zone that is called as the ZRWA area. I'm going to talk about it in a little bit more detail in the next slide. Here we see the random write zone, which is around 1 MB of size, which will get the data from the applications through that channel in a random way. But when it is going to purge into the zones, it is going to do it sequentially. I'm going to talk about it. Let's see a pictorial representation in the next slide. So this is a high-level diagram of what is a zone. At a low level, I'm going to be representing at a die level, or you can say at the NAND flash cell level. It's just a collection of blocks. So talking about the stripe set here, basically zone, there are two types of drive types, the ZNS drive types. One is the no rate zone, the other one is the rated zone. So this one, if you see here, 31 data zones and 1 parity zone, if you see, this is depicting a rated ZNS drive. No rate ZNS drive is the complete zone. The complete zone is a drive here. I mean, basically a drive is not divided into multiple zones on those kind of drives. It's just one zone that will be at the whole drive level. Let's move on to the next slide. So this is what I was talking about. So if you see here on the left side, namespace 1, conventional namespace, that is 4 MB. It's a RAM here. So each zone will have this namespace 1 basically available for metadata. This is something like a metadata area where we are gonna store the reads and writes for the metadata. And on the namespace 2, if you see here, there are multiple zones which are written sequentially. And if you see here, the write pointer, so every time a zone is open, it is associated with a write pointer. which will let us know where do we write the data into the zone. So once we have this ZRWA area filled, area is write anywhere, random write area. So here we are going to write data to LBA 0, LBA 10, LBA 100, LBA 1000, whatever it is. And next, when it is writing into the zone NAND, here what happens is, once this is just the ZRWA area is full, if it is just little above 1 MB, what this is going to indicate to the zone NAND is this will purge the data into the zone NAND, and the write pointer here is going to be enhanced to that next pointer, next available sequential LBA. So the write pointer is going to be enhanced to that point, so that whenever we have the next ZRWA written here, and next purging will happen to the, from the, let's say we have written 1 MB of data, the next available write pointer should be after 1 MB. So next data is going to be written like this. So it happens like this way once the zone is full. So normally what happens is, the zone will again be available for writing only at two stages or states of zone. One is the empty state, or we have to reset the zone. That's when we'll be able to write on the zone again. Hope this is cleared. Let's move on to the next slide. So here I'm just going to talk about the endurance management, one of the technical proposal that was going on. So this depicts the examples of the ZNS configurations. So if you see the simple NVM subsystem here, the endurance is managed across all media units, and maximum bandwidth is allowed, is achieved here by allowing the read and write operation to simultaneously access all the media units. So if you see here, this is one set, and this is the endurance group 1. And all of the NAND flashes or cells are in the same endurance group here. So this is basically a simple NVM subsystem, not a dual one, does not handle the HA here. There are few requirements where they need maximum bandwidth, so they use such kind of configurations. So when we talk about the dual NAND NVM subsystem, so what happens is, so this is operated in a QLC level here now. So the media units, which is capable of being operated as QLC, they divide this set into two sets here. So these are channels, and what happens is, each cell on this channel, so all the 4 channels on each cell, the first 4 NAND flashes are grouped as one set, and the second set here are having this multiple flash cells. So the first set will be operating as a SLC, and the second one, if you see, it will be operating as a QLC. So there are few configurations wherein we require the vertically organized NVM subsystem. So if you take the example here, the controller has 4 channels, and each channel has the cell. So I mean, so if you see here, the flash cells are organized in a vertical way here, and all of them are grouped as one set, and that set is considered as a endurance group 1, 2, 3, 4. So if you see here, endurance is managed separately for each set. So being media units being shared, channels are allocated to the same endurance group. The bandwidth for NVMe set here is should be less than or equal to the bandwidth of the channel on that NVM set. So these are 2 or 3 ZNS configurations that are being used by multiple vendors. Few of them. So, but most of the cases in the market today are with dual and vertically organized NVM system. Simple NVM subsystem, very less use cases are there. So now let's talk about the zone states. So the zone state machine looks something like this. So initially when we have the ZNS, it's empty. So once we have the zone opened for reading or writing sequentially, so there are two ways of opening a zone. One is implicitly opened. The other one is explicitly opened by the zone command. It could be an append or the write command, which we talk about in the earlier slide, which was discussing about the ZNS architecture. And so once we have the zone that is in open state, and we write the data onto that zone, and once that zone is full, we close that zone. So the zone is closed and it moves to the full state once it attains the maximum LBA. Once the zone is returned to the maximum LBA and that zone is full. So the zone is closed and it is moved to the full state. So once the zone is full, depending on the requirement, the zone can be moved to the empty state only by either reset, or we have to move that data from that zone to another zone, like basically writing that data from that zone to another zone and then resetting the existing zone. So this is the allowed zone state transitions. And we can see this happening while doing the testing by using this PEG NVMe control commands. We have seen this happening. So we have seen the zone opened, zone empty, zone full, and zone closed states by using those commands, PEG NVMe control commands. And we can test various conditions there. Like we may, like a race condition could be tested, and the zone full condition could be tested. All those kind of test cases around the zone states could be designed and we could be tested. Yeah, this is a diagram that depicts something, I mean, from the empty state to the full state, what happens when there is a zone is empty. So if you see here, the zone was empty. Now we have the zone in the opened state, and the 64K of data is present in the ZRWA area that is being purged onto this. And if you see here, there is a minimum write area here that is being purged onto the open zone here. And the right pointer, if you see here, initially it was here. When the data is written, the right pointer is going to be advanced, or it is going to be pointing to the next available LBA here on the zone. These are still in open state. So now this is, if you see in the red here, the zone here, the ZRWA area here is full and it is ready to be purged onto the open zone here. Yeah. And next, we see the zone closed here on the zone closed state. The right pointer here, it says there is some data in this zone, but it is in closed state. Next, the zone is full. So if you see on the right side, there are empty, open, closed, full, offline states. And these are the zone commands that we are going to use. So commit, right pointer, all that. This is on a SLC. So if you remember the previous slide, this one. This is a SLC. So this is an example of that kind of an configuration. So like I said, during low-level representation of the zones, it is at the flash level. We had one of the slide where I talked about the two different drive types. So one is the no RAID on drive. So one host drive zone is 32 zones on a drive. There are vendors or the companies that are working on this kind of configuration using the Samsung drives, wherein host is creating RAID on the drive with 31 zones as data zones and one zone as the parity zone. And there are few other vendors like WDC, SK Hynix, and Kioxia, where one host drive zone is one zone on drive. We will see the pictorial representation of how it is there on the next slide. So it's something like this. If you see here, this is a WD, where the complete zone is one stripe here. So if you see the sizes, the size of a zone on WD drive is on a 2 terabyte drive would somewhere be around 2 terabyte. But if you see this on a Samsung drive, you are going to see 32 zones here, which is 31 zones are data zones, and one zone is the parity zone, the 31st zone. So this is the ZNS stack. Hope this is not an in detail, not to the core level of the understanding of ZNS, but we try to give a high level understanding on what is ZNS, how it is being useful in the market today to reduce the cost of $ per GB, and the type of zone drive types, and to some extent the zone functionality of the ZNS drives. So just to recap on what we have talked about, me and Arup. So basically the ZNS drives are the zone namespace drives is a specification wherein we are trying to which tries to dictate some of the SSD firmware functionalities like wear leveling, garbage collection, with the ZNS, the zone management, create and delete, the IO scheduler, all those goes as part of host, which will help in reducing the write amplification, space amplification, and the usable storage capacity on the drive will increase at least on a range of 10% to 50%, I would say. So which will helps in the over provisioning part of it is also reduced, because of the reduced write amplification and the space amplification, the over provisioning is reduced, and which will enhance the life of the SSD, as well as the cost of the drive is reduced. Not drive, cost of the data that we are storing on a drive is reducing, so which is directly impacting the market scenario wherein the data is growing substantially today. So we try to cover as much as we can at a very high level, and to some extent at the technical level. So these are some references from where we got this. Thank you, everyone, from me and Mindtech. So let's get into the chat session.